So a 1035 steel has a tensile strength of 80 psi and is to be used for a part that operates at a temperature of 750 Fahrenheit. Okay. Estimate the endurance limit. So when this endurance limit, it is SE, which is we want to compute. When at the operating temperature, if only the tensile strength at room temperature is known, at the room temperature of 70 F, the endurance limit for the material is found to be SE prime equals 39 psi. So there are two sorts of things going on. Let's solve them one at a time. So part A. Okay, let's focus on the first part. Only the tensile strength at room temperature is known. So actually that's given to you. So the tensile strength at room temperature is 80 psi. The room temperature seems to be 70 Fahrenheit. So the tensile strength SUT, okay, which is, let's call that RT, which is RT is room temperature. So SUT at 70 Fahrenheit is 80 psi. Okay, that's given. So we are asked to compute the endurance limit at the operating temperature, and the operating temperature is 750 Fahrenheit. So what we want to compute here is the endurance at 750 Fahrenheit. Let's call that SET. T is operating temperature. And so we asked to compute SE at 750 Fahrenheit is unknown. Okay, so this is a problem where the lab specimen is tested at room temperature or 70 Fahrenheit, and the actual specimen is operating at 750 Fahrenheit. So there are factors associated with the temperature which will change the endurance limit. It will no longer be the endurance limit of the specimen in room temperatures because of the temperature. So we can flip some pages back and go to the empirical data for let's see, I think it's K. Okay. So here it is. This is a temperature factor KD. This gives a method to compute the endurance for temperature effects. So I've outlined the sort of the recipe here. If the endurance is unknown, SE prime is unknown, then this is what you do. You first estimate ST divided by SRT from the formula here. Then we estimate the SUT, this is the endurance, this is the ultimate strength at operating temperature using this formula. Then finally, we'll compute SE prime using these formulas. So just put this into action. Okay, so what we'll do is we'll follow this recipe for first case when SE prime is unknown. So if SE prime is unknown, this is what we do. Step A, let's go back to KD. We need to use this formula, so I'll copy it down. Now here we are dealing with Fahrenheit and not Celsius, so I'll use this formula. Okay. So I'm just following this A through C actually. This is from KD. data. Okay, so here we are. S at T divided by S RT is 0.98 plus 3.5, 10 to the negative 4. Our temperature here is to be substituted in Fahrenheit, so it's 750 minus 6.3, 10 raised to negative 7, 750 square. Okay, so this will give us 0.89. Well, you could actually write what ST is. ST is pretty much 750 and SRT is pretty much 70. This is 0.89. Okay, that's step one. Step two is we need to estimate SUT at operating temperature using this formula. So I'll copy this formula and then go around using it. Step B is SUT at operating temperature is the ratio ST divided by SRT times SUT at room temperature so SUT at 750, that's the operating temperature. This ratio is 0.89. And then SUT at room temperature is given to us. It is 80 kpsi so it's 80 kpsi. So this gives us SUT at 750 is 71.2 kpsi. Okay, and then the final step is to actually compute the endurance limit. So for that, we go back to KD and notice that you can estimate SC using either of these two formulas. Here we're dealing with kpsi, so we'll use this table. So I just copy it down. Let's take this. So this is part C. This is our formula. Okay, so what we know here is that SUT at 750 is 71.2. At 750 is 71.2 kpsi. We notice that 71.2 is less than 200 kpsi, which is less than 200 kpsi, which means we need to use this formula, the first one, SE prime is 0.5 SUT at the operating temperature, so it'll be 0.5 SUT at 750, which is 0.5 times 71.2. So our final answer is SE prime is 35. So SE prime, if you want, you could also write it at 750 or at, well, we could write this as SE prime at T or SE prime at, the T is here 750. So this is 35.6 kpsi. Okay, and then I think there's a third step. It says if K in the final step is KD is 1, SE is SE prime, so we can just write that down. D is that KD is 1, not that it was asked, but we just write it down. SE prime, so that is 35.6 kpsi. Okay, that's the answer. Okay, so let's move on to the second part of the question. Okay, so that's now figured out. Now, at the room temperature of 70 F, the endurance limit for the material is found to be SE prime is 37. This is a case where you know what the SE prime is, perhaps from a lab experiment. So let's write that down. So for the second part, SE prime at room temperature, which is let's write RT, or SE prime at 70 is given to us. It is 39 kpsi. So if SE is known at room temperature, there's a different set of formulas you need to use. Let's look at those formulas. So this is when SE prime is unknown. The second case is SE prime is known. That's the case we're looking about. Here we again estimate ST divided by SRT using the same formulas. Nothing will change. Here KD is ST divided by SRT. And then finally SE is KD times SE prime. So let's use this. So this is case 2. SE prime is known. So the first step is estimate ST divided by SRT is S750 divided by S70 is point, I believe 89. Uh, yeah, it's 89. So we can just say here, I'm just going to say same for part I. Yeah, C part 1. The second step is to estimate KD. So again, go back to this. This is the method, estimate KD. So I'm going to do that. KD is ST divided by SRT, which is 0.89. The third step is estimate SE as KD times SE prime. SE prime is KD times SE. So here actually it's 750. This is at 70. Switch this, so it will be SE prime. This is 0.89 times, this is already given, 39. So SE at 750, by the way, this comes out to be 35 kpsi, and so the answer is SE at 750 is 35 kpsi. Okay, not too far from this answer.